The anniversary of Mount St. Helens erupting has some people pondering when our own Mount Rainier may blow, and there are signs it's waking up.
Mount St. Helens, located in Washington state, is one of the most well-known and active volcanoes in the United States. It gained international attention after its catastrophic eruption in 1980, which dramatically reshaped the landscape and caused extensive destruction. The eruption was one of the most significant volcanic events in American history, taking with it 57 people and covering vast areas with ash. Recently, there has been a resurgence of seismic activity beneath the volcano, raising concerns that it could be preparing for another eruption. Advances in technology have introduced new ways to monitor volcanic activity more accurately, allowing experts to predict eruptions 3 days in advance, and it's not looking good. In this video, we're going to bring you face-to-face with all of it.
Others were more intrigued than they were worried about the mountain's latest antics.
It's been active for a while. Since February, Mount St. Helens has been at the center of intense seismic activity, signaling a possible shift in its volcanic behavior. A surge in seismic events has been documented, with more than 350 earthquakes recorded beneath the volcano's surface. Most of these were small, above 95% of them measuring below magnitude 1 on the Richter scale. These tremors are considered minor, often too small for humans to feel, but the constant occurrence of these low-magnitude quakes raises concerns due to the sheer number and frequency. Despite the predominance of minor tremors, seismic activity began to intensify starting in early June. In just 1 week, 38 tremors were recorded, marking an unusual uptick in volcanic activity. This significant jump in frequency, although still comprising small quakes, suggests something is shifting below the surface of Mount St. Helens. By comparison to previous years, the frequency and intensity of these earthquakes have significantly exceeded expectations for a volcano of this type and location, particularly when considering the dormant period Mount St. Helens has experienced since its eruption in 1980. A key factor in understanding the potential for a larger eruption lies in the depth at which these quakes are occurring. Studies show that the seismic activity is originating about 3 to 4.6 miles beneath the summit of the volcano, deep within the Earth's crust. Volcanic earthquakes are typically associated with the movement of magma beneath the surface, and deeper activity, such as this, indicates magma or pressure from the lower levels of the crust is slowly making its way toward the Earth's surface. Such depths are consistent with magma migration, a typical precursor to further geological activity, whether an eruption is imminent or not. Many experts suggest that this heightened seismic activity could be attributed to a combination of rising magma and increased stress on underground rock formations. With the ongoing pressures in the magma system, minor earthquakes are becoming more frequent and could eventually escalate to more significant events. While these smaller quakes may not indicate immediate eruption risk, their persistent nature calls for cautious monitoring, particularly when considered alongside the behavior patterns of similar volcanoes. A recharge event. The term recharge is widely used in the context of active volcanoes like Mount St. Helens to explain the natural and complex processes involved in volcanic behavior. Recharge refers to the movement of magma from deeper into the Earth's crust toward more shallow magma chambers or reservoirs beneath the volcano. As magma accumulates, it adds pressure to the surrounding rocks and can ultimately trigger more tectonic activity, such as earthquakes or even more violent eruptions if the magma fails to find a safe path to escape. While recharge events are not uncommon in the life cycle of an active volcano, recent observations at Mount St. Helens raise new questions about the intensity of the buildup. The recent seismic trends have suggested that the volcano's magma reservoirs might be filling up more rapidly than anticipated as magma pushes upward toward the surface. Volcanoes like Mount St. Helens typically experience intermittent periods of recharge, with magma flowing up in pulses over long spans of time. However, when these events occur closer together or at a higher volume, it suggests that the pressures beneath the volcano are mounting and that an eruption might soon become more likely. Recharge events have direct geological implications, as the rising magma begins to press against older volcanic structures and formations, increasing tension between layers of rock. This buildup of pressure increases the likelihood of earthquakes, which are signals that rock layers are under intense stress and fractures are appearing in the crust. The quakes that occur during these recharge events often serve as signals to volcanologists that something major may be happening beneath the surface. While minor earthquakes themselves don't necessarily mean an eruption is inevitable, the frequency and magnitude of these smaller quakes play a significant role in tracking volcanic behavior. With such seismic activity occurring near volcanic hotspots like Mount St. Helens, scientists have to carefully monitor the situation. More than ever before, geologists are beginning to recognize how the interaction between earthquakes and magma during recharge events can influence eruption predictions. While minor earthquakes may be harmless, the cumulative stress they represent cannot be ignored, particularly as the pressure begins to build. What increases the risk in this case is the relative intensity of the recent seismic activity. In previous years, the volcano's behavior was generally calm, but as magma rises deeper into the Earth's crust, these recurring earthquakes have created concern among experts. They believe these movements can serve as both an indicator of volatile magma movement and a signal of potential changes within the rock layers near the volcano's surface. How recharge causes increased stress in rocks. The mechanism by which magma creates stress within the Earth's crust is critical to understanding the current seismic activity at Mount St. Helens. As magma accumulates, it forces its way upward through porous rock and towards the surface, gradually filling subterranean chambers and generating high pressure along fault lines. This rising magma, with its increased volume and heat, begins to cause existing rock formations above it to bend and crack, leading to the earthquake activity that has been seen over the past year. When magma rises, it doesn't always find a direct path to the surface, and the pressure starts to concentrate in specific areas within the underground reservoir. As the pressure continues to build, the geological stress at certain focal points can cause fractures and faults in surrounding rock layers. These fault movements manifest as earthquakes, often felt as small tremors, but in some cases may escalate into more noticeable seismic events. During recharge events, particularly with increased seismic activity, these cracks in the Earth's crust are stressed even further, making it more difficult for magma to escape or find release routes. If the pressure from magma becomes too great and surpasses the ability of rock formations to withstand the pressure, this can eventually lead to explosive volcanic eruptions, though such outcomes are difficult to predict with certainty. In some cases, however, the magma may flow quietly from a volcanic vent without an eruption, releasing much of the pressure in the process. In the case of Mount St. Helens, the recent seismic activity, including smaller earthquakes along the nearby fault lines, has highlighted that the volcanic system is, at minimum, going through a cycle of building pressure. Understanding this process is key in tracking whether these activities will lead to an eruption or if they are simply part of the cyclical behaviors often seen in active volcanoes. The current data doesn't confirm an immediate eruption, but it does signal that Mount St. Helens is far from dormant. Whether this is the start of something larger, such as a more catastrophic eruption, or part of an ordinary recharge cycle, remains to be seen. But the thing is, it's not that simple. Magma movement and accumulation. Beneath Mount St. Helens, the process of magma movement is a complex and gradual one, requiring careful scientific study to understand. Magma begins its journey from deep within the Earth, roughly 16 miles beneath the surface, where intense heat causes rock to melt and form molten material. As magma moves upward, it encounters several different layers within the Earth's crust, slowly accumulating in reservoirs about 2.5 to 6 miles beneath sea level. These underground chambers, or pockets, act as pressure points for the movement of magma toward the surface does not happen in a single burst, but rather occurs in incremental steps over time. This process can span from weeks to decades, depending on the specific dynamics beneath the volcano. Over time, the pressure from the accumulating magma slowly increases. Although magma movement typically happens gradually and quietly, it can lead to small earthquakes, particularly as magma disturbs or fractures surrounding rock formations. While the rising magma builds pressure, there are often no immediate signs of eruption, meaning that eruptions may only occur after significant amounts of stress have accumulated in the system. For Mount St. Helens, such gradual changes might be alarming, but they are not necessarily a direct signal that an eruption is inevitable. This constant magma movement does lead to geological changes beneath the surface, such as the creation of new volcanic conduits, fractures, and fissures within the surrounding rocks. However, in general, Volcanic systems like St. Helens go through extended recharge and refilling cycles without explosive consequences. The behavior beneath Mount St. Helens, while being actively monitored, remains relatively consistent with typical recharge activities observed at other active volcanoes. Still, each instance is unique and requires detailed analysis to understand fully whether the activity represents typical behavior or if it signals a more dangerous situation. The United States Geological Survey, which monitors Mount St. Helens closely, has been tracking the increased seismic activity since its onset, attempting to assess whether these events could lead to more significant volcanic eruptions. According to the USGS, while the current seismic patterns are notable for their frequency and depth, they fall within what they call normal background seismicity for a volcano of Mount St. Helens type. This term refers to seismic events commonly observed in active volcanic regions that, while significant in the short term, do not necessarily herald an imminent eruption. The USGS emphasizes that the eruption events seen in 1980 were catastrophic, but since then, seismic activity beneath the surface of the volcano has fluctuated, with varying intensities of magma movement and earth-shifting seismic events occurring regularly without triggering eruptions. As the USGS points out, the ongoing tremors are consistent with a behavior pattern seen during historical recharge events at Mount St. Helens. Recharge events refer to when magma gradually returns to the magma chambers below the volcano, accumulating over time and creating potential pressure for future volcanic activity. These types of events are characteristic of active volcanoes and have been documented in Mount St. Helens several times since the 1980 eruption. Historically, such events have not always led to eruptions, indicating that not all periods of seismic activity are directly connected to surface activity. Given the data, scientists argue that while the seismic activity is heightened compared to previous years, it is still well within the parameters expected for a volcano like St. Helens during a recharge phase. However, the USGS continues to study the data carefully, aware that any changes to this pattern could lead to changes in volcanic activity, and there's a lot that could lead to it happening. Possible triggering factors for seismicity. Several potential factors might explain the recent uptick in seismic activity at Mount St. Helens, ranging from influxes of new magma to pressure buildups caused by the cooling residual magma from the previous 1980 eruption. The introduction of fresh magma into the volcano's magma chamber is one possible cause for the shaking observed over the past several months. When magma is injected into existing reservoirs, it can disturb surrounding rock structures. The magma's pressure and thermal energy may cause the rock to crack or shift, generating a series of seismic tremors. These shocks are a warning sign that magma is moving within the Earth, often carrying heat and gas with it. New magma entering a magma chamber can effectively recharge the volcano, preparing it for potential activity, but it does not guarantee an eruption. In many cases, the magma may simply accumulate without breaching the surface. Another consideration is the residual magma left over from the violent eruption of 1980, which continues to cool and settle. When magma cools, it undergoes both contraction and solidification, which can lead to changes in the stress conditions beneath the surface. Cooling magma creates gas pressure as volatile components within the molten material attempt to escape, sometimes through fissures in the crust. This buildup of internal pressure can also trigger small earthquakes, like the ones recorded recently. The magma may not need to be actively rising for its residual cooling to contribute to seismic activity. Experts suggest that as the magma's residual heat dissipates and the internal gases shift, even these older, slowly cooling masses of magma can play a role in disturbing surrounding geological structures, leading to increased seismicity. While these seismic tremors are not large enough to lead to an eruption immediately, the underlying factors that cause these shifts, whether new magma influx or residual pressure, are indicative of an active and dynamic volcanic system. As Mount St. Helens continues to rattle and shift beneath the Earth's surface, scientists will keep monitoring these phenomena, closely watching for patterns that might indicate a more dangerous event is building up below. It all has happened before, too. The history of Mount St. Helens is defined by its dramatic eruptions, with the catastrophic 1980 eruption standing as one of the most significant geological events in US history. On May 18, 1980, a massive eruption triggered by a landslide on the volcano's north face devastated the surrounding area. The eruption sent an enormous ash cloud over 80,000 feet into the sky, covering nearby regions, disrupting air traffic, and causing significant damage. The explosion released an energy equivalent to 24 megatons of TNT, and its subsequent landslide removed over 1,300 feet of the mountain's summit. The eruption caused 57 deaths, destroyed thousands of acres of forest, and left a lasting impact on the environment and surrounding communities. In the aftermath of the 1980 eruption, Mount St. Helens remained active, with several smaller eruptions over the decades. The most notable of these occurred between 2004 and 2008, when the volcano exhibited ongoing volcanic activity without producing an immediate catastrophic eruption. This period, characterized by moderate eruptions, was marked by the slow extrusion of lava and the continuous release of gas from the volcano's crater. These smaller eruptions provided researchers with an invaluable opportunity to observe volcanic behavior in a relatively controlled manner, without the catastrophic risks seen in 1980. During the 2004-2008 period, volcanic monitoring systems had been significantly improved since the 1980 eruption. A greater understanding of magma movement and behavior led to the development of more advanced seismic and geophysical monitoring techniques. These advancements allowed scientists to more effectively track the volcano's movements, detect precursory seismic activity, and predict eruptions with greater accuracy. For example, scientists were able to closely monitor the slow extrusion of new lava within the crater, which provided vital information on how Mount St. Helens might behave in the future. By studying the activity during these smaller eruptions, scientists gained a deeper understanding of the complex processes governing the volcano's behavior. Observations showed that magma didn't always rise to the surface explosively. Instead, it could extrude gently, forming new lava domes. This helped clarify that the eruption of 1980 was an extreme event and that the volcano might follow a less violent path under certain conditions. In addition, scientists refined their models of how volcanoes change over time, including insights into factors that may lead to a much larger eruption under specific circumstances, just like it has in the past. Seismic comparison. One of the most telling aspects of current seismic activity at Mount St. Helens is its contrast to past periods of increased seismicity, particularly in comparison to the months leading up to the 2004 eruption. In the years prior to the 2004 to 2008 eruptions, Mount St. Helens was characterized by high-frequency seismic events. These tremors were particularly prevalent in early 2004, with increased seismicity marked by 1 to 2 small earthquakes per minute. The constant swarms of minor earthquakes indicated significant magma movement beneath the surface, and were a clear signal of the buildup of pressure and an imminent eruption. Many of these seismic events occurred within the upper 3 miles of the volcano, near the site where the magma was pushing upwards. Seismic data from this period was used to refine predictions and allowed scientists to forecast and confirm that volcanic activity was building towards the eruptions observed between 2004 and 2008. In contrast, the recent seismic activity at Mount St. Helens, since February, has involved a slower rate of earthquakes. These tremors have been observed to occur with an average frequency of about 1 per minute, which is notably lower than the high-frequency tremor swarms experienced in the early months of 2004. While the recent tremors continue to be significant, they don't compare in magnitude or frequency to those seen before the 2004 eruption. For now, these tremors can be viewed as relatively minor compared to what happened during the larger, more intense phase of volcanic activity prior to 2004. This difference may indicate that magma is moving, but the process is slower, and the volcano might not be at risk of immediate catastrophic eruption, at least in the same manner as it was in 1980 or during the 2004-2008 eruptions. Another key difference is the depth of seismic events. Seismic data shows that many of the recent tremors have originated 3 to 4 miles beneath the volcano's summit. This depth is considered relatively shallow in the context of seismicity caused by magma movement, but it is significantly deeper than some of the events observed before the 2004 eruption. During that time, seismic activity was much closer to the surface, suggesting magma was making its way up towards the surface much faster. The reduced frequency and depth of the current seismic events suggest that the recent seismic activity could be part of the normal recharge process that volcanoes like St. Helens experience. However, scientists cannot rule out the possibility that, if the tremors continue, they may signify an escalation towards more significant activity, though that remains a possibility that the data has yet to support fully. In conclusion, while there are notable differences in the seismic activity leading up to the current monitoring period and prior eruptions, Mount St. Helens remains an active, dynamic volcano that requires continuous observation. Though current seismic patterns may not suggest an imminent eruption on the scale of past events, they still offer valuable insight into the workings of the volcano and may provide critical information should the situation change. The lessons learned from both the catastrophic 1980 eruption and the smaller eruptions of 2004-2008 have equipped scientists to better understand and anticipate the volcano's behavior, ensuring they are prepared for whatever may come, because this volcano has been fairly active recently. November 28, 2023. Earthquake. On November 28, 2023, a minor earthquake struck near Morton, Washington, with an initial reported magnitude of 2.3, later revised to a lower magnitude of 1.2. While this earthquake was small, its location caught the attention of geologists due to its proximity to Mount St. Helens. It was determined that this tremor was unrelated to volcanic activity occurring deep beneath the surface of the mountain, but the event nonetheless shed light on the complex seismic dynamics of the region. The earthquake near Morton could be attributed to the broader tectonic forces at play in the Pacific Northwest. Despite the small magnitude of the event, it serves as a reminder of the area's significant geotechnical complexity. The shifting of tectonic plates along fault lines in this part of the world is an ongoing process, creating both volcanic and seismic events that can be hard to predict. This earthquake, while not directly linked to Mount St. Helens, could represent part of the larger seismic network that extends through the Cascadia region, where complex interactions between various fault systems occur. These events can be indicative of ongoing tension and pressure accumulation within the Earth's crust, something that can influence volcanic activity without being directly related to it. Seismic complexity in the Pacific Northwest. The Pacific Northwest, including the area around Mount St. Helens, is part of a tectonically active region influenced by multiple complex geological forces. One of the key geological features in the region is the Cascadia subduction zone, where the Juan de Fuca plate is slowly being forced beneath the North American plate. This massive plate boundary is responsible for much of the region's tectonic activity, including both earthquakes and volcanic eruptions. The Cascadia subduction zone has long been a source of concern for geologists, as it is capable of producing major earthquakes with magnitudes exceeding 9.0. However, the tectonic stress in this region also plays a crucial role in triggering volcanic events, especially at Mount St. Helens, located near the northern edge of the CSZ. Seismic events, even those far from the volcano itself, can be connected to the tectonic tension building within the subduction zone. Minor tremors, like the one near Morton, could reflect the readjustments that occur along these fault lines, which can, in turn, influence the volcanic activity of nearby systems, such as Mount St. Helens. Though Mount St. Helens is not positioned directly along the subduction zone, it is part of the volcanic Ring of Fire, a region shaped by tectonic collisions and seismic activities around the Pacific Ocean. The tectonic forces that drive magma up to the surface and lead to volcanic eruptions are intricately tied to the regional seismic activity. Shifting plates create not only earthquakes, but can also influence magma movement, potentially triggering a response at Mount St. Helens and other nearby volcanoes. Recent seismic activity in the region suggests that the tectonic environment remains active and evolving. The recent earthquake near Morton is a sign of ongoing strain and stresses in the Earth's crust. These stresses, while not immediately connected to deep-seated magma movements beneath Mount St. Helens, could still play a role in altering conditions and raising the risk of future volcanic or seismic events in the broader Cascade Range. Understanding these regional tectonic dynamics is crucial for volcanologists as they continue to monitor seismic events in the area, helping to decipher the potential for future eruptions or earthquake activity that could influence the behavior of Mount St. Helens. The possibility of a future eruption. Mount St. Helens is one of the most well-known volcanoes in the United States due to its catastrophic eruption in 1980. Although the eruption dramatically altered the landscape, including the loss of 1,300 feet in height and the creation of a massive crater, Mount St. Helens still retains the potential for future eruptions. The question remains whether it could erupt explosively in the same way it did over 4 decades ago, or if its physical changes in the aftermath of that eruption will influence future events. One key factor driving the explosiveness of volcanoes is the buildup of pressure within the magma chamber. When magma accumulates beneath the Earth's surface, it can become pressurized, and if this pressure exceeds the structural integrity of the volcano, an eruption may occur. This explosive potential depends on the viscosity of the magma, its composition, and the amount of dissolved gas it contains. Magma's viscosity, how thick or sticky it is, plays an important role in whether an eruption will be explosive. Highly viscous magma tends to trap gas, leading to a greater buildup of pressure and a higher chance of a violent eruption. In contrast, magma with low viscosity allows gas to escape more easily, resulting in less explosive events. The magma that Mount St. Helens produces is relatively viscous, which contributed to the explosiveness of the 1980 eruption and could do so again under certain conditions. Changes in the structure of Mount St. Helens since the 1980 eruption may influence how future eruptions unfold. After the 1980 eruption, which drastically altered the mountain's elevation and form, the volcano now has a massive crater where the previous summit once stood. This crater, formed by the collapse of the summit during the eruption, has essentially created a bowl-shaped depression in the land, which provides a new, accessible space for magma to accumulate. The new crater may serve as a more efficient pathway for magma to rise toward the surface compared to its pre-eruption structure. This might alter how quickly magma is released during an eruption, although it does not change the primary factors that influence the volcano's explosivity. Furthermore, the magma storage areas beneath the volcano have likely shifted in the years following the eruption. While magma still rises from deep within the Earth, around 16 miles beneath the surface, the pathways and the depth at which it accumulates before finding a way to escape could influence the intensity and type of future eruptions. Mount St. Helens remains capable of causing eruptions on a similar scale to the 1980 event, provided that the right conditions align. If magma continues to accumulate beneath the surface and gases build up within the chamber, the pressure could eventually overwhelm the volcanic structure, leading to an explosive eruption. The fact that magma rises from depths of up to 16 miles makes it a continuous process, and these ongoing seismic tremors may serve as early warning signs of heightened pressure. While smaller eruptions in recent years, such as those between 2004 and 2008, did not reach the violent scale of the 1980 eruption, the potential for a future, larger eruption remains. As such, scientists must remain vigilant in monitoring the volcano's seismic activity, gas emissions, and ground deformation to better understand and prepare for what could come. The future explosivity of Mount St. Helens will depend on many variables: magma composition, internal gas buildup, and the physical structure of the volcano. Though its appearance has changed, Mount St. Helens retains the intrinsic capability for catastrophic eruptions. It is crucial that monitoring efforts continue to focus on understanding the various factors that could drive an event similar to what took place in 1980. Whether or not the eruption would be as explosive as the one that devastated the region is still uncertain, but it is clear that Mount St. Helens remains one of the most active and carefully observed volcanoes in the world. Continued research into volcanic eruption processes helps better predict not just the likelihood of an eruption, but also the type of eruption that could occur. With sophisticated instruments capable of detecting subtle gas emissions and changes in thermal activity, scientists can anticipate the potential hazards associated with an eruption within days of it happening, whether they involve pyroclastic flows, lahars, or significant ashfall. Understanding these hazards allows communities to better plan for their specific risks, improving preparedness. That's something we can't compromise on, because if we look away, we could potentially find ourselves in a situation we won't be able to run away from. What do you think? Leave your thoughts in the comments below, and if you like this video, don't forget to subscribe to our channel. See you in the next one.